Okay, hello, honor students. Welcome to your lecture on the ideal gas law. We are in our unit on intermolecular forces. And what often goes in traditional chemistry textbooks is what we do is we kind of do a subcategory dive into gases and their interactions between their gas particles. So a very specific subsect of intermolecular forces where we specifically focus on gases. So that's what we're going to teach you today. So first and foremost, let's talk about some of the properties of gases. So gases, as you know, are low density. They're low density samples of particles, right? There are not many particles are in a unit of space. Many are colorless and have no odor. Many, not all. You know what I'm talking about. They can form solutions. So you can have gas mixtures, right? Can form solutions in any proportions, in any ratio, in any proportions or ratio. And finally, by studying the property of gases, we see that there is a relationship, a mathematical relationship between volume, temp, and pressure. Okay, so that's kind of some general information about gases. Now, you probably have heard of the term gas pressure or vapor pressure, and there's actually a slight difference. So vapor pressure is the pressure due to the particles above a liquid sample that have entered the gas phase. But gas pressure is pressure due to the collisions of a gas sample particles. So there's a slight nuance difference there. If you're like, don't worry, it's not a huge thing. It's just something small that I wanted to add in. So what we do is we describe the behavior of gases through what we call gas laws and theories of motion. So I'm going to introduce to you a theory on gases and a few gas laws that take those assumptions of the theory and put them into a mathematical relationship. So we like to think of gases as being ideal. Now, as we know, a lot of science is here's the theory, what do we actually see in the experimental lab? And there's always a little bit of a difference, right? There's error, there's other factors that we don't account for, right? But it's very common practice in chemistry and in science in general to present a theory that is substantial and credible and used to predict, and then compare it to what we actually see in the lab, recognizing that we will see points of differentiation or differences. Okay, so let me unpack the ideal gas, what we use to develop our mathematical relationship on. So an ideal gas, okay, is a gas that, I don't think I left myself enough space. An ideal gas is a gas that has no IMFs between particles. Okay. It's also a gas whose particles move in constant straight line motion. In constant straight line motion. For those of you in physics, right, we call that vector motion. And what we say is that with ideal gases, collisions are elastic. That means there's no energy transfer. There's no energy loss and there's no energy transfer. okay, when particles collide. So these are kind of like the premises of what an ideal gas behaves like, okay? And we tend to see gases behave ideally at super high temperatures and very low pressure conditions. Okay. Super high temperature and very low pressure conditions or surroundings is when we get to see this. Okay. And let's see if I can. Oops, that's not what I wanted. Okay. So, because when they are spread out, this is because when they're spread out with low forces and negligible volume, okay, we can tell, we can predict that there will be very low intermolecular forces, right? If you have a ton of space between your particles, very small particles that are moving super high, super fast due to high temperatures, you don't have anything condensing them together, you're not going to get very many IMFs between them. That means the faster they're moving, the more likely they are to move in straight line motion. And when they do collide, the more likely they are to skim past each other and not get stuck, right? We also see that gases behave in an ideal manner when they're at super low mass, okay? When they're super, super small particles. So like a hydrogen gas sample would probably behave more ideally than like a bromine gas sample because bromine is simply bigger, which means there's more electrons, which means there could be more LDFs, IMFs that stick the two particles if they were to collide, right? In the actual world, right? Not in the theoretical, but in the actual. So we like to say that super low mass, super, super small particles are more likely to demonstrate ideal behavior. So when we talk about ideal gases, and under these assumptions, okay, and conditions, we have developed a relationship between four variables. The four variables are the amount of moles or the amount of particles, and I'm going to introduce what a mole is in the future. The amount of particles, okay, the pressure value in ATM, atmospheric pressure, okay, the volume that the gases take up, the volume that the gas particles occupy in liters, and the temperature, right? And we actually measure this in Kelvin. So remember that Kelvin is a new unit of measurement that I've briefly mentioned before. And to go from Celsius to Kelvin, you do the degree Celsius plus 273.15, and that gives you the value of temperature in Kelvin. So let's break it down into three individual gas laws that relate two of these variables at a time. And then I'm going to give you a combined gas law that includes all four of these variables, known as the ideal gas law. So the first kind of two variable relationship they're going to explore is known as Boyle's law. And by the way, all these laws are totally named after the scientists who discovered them. So Boyle's law tells us that when you have mass and temperature constant, okay, then pressure and volume have an indirect relationship. Okay, so that means that when we look at our equation, we can say that the pressure and the volume in one condition equals the pressure times the volume in another condition. So that means conceptually, if I increase pressure, I'll see a decrease in volume. And if I increase volume, I'll see a decrease in pressure. Okay. And that can be reflected through this mathematical equation with actual values, pressure in ATM, volume in liters. Okay. So let's connect this to something that's more tangible. Like, okay, what does that actually mean? Well, let's think about how we breathe. Well, when we breathe, what happens is that the volume of the lung increases, right? When we inhale. Okay? And as a result, pressure decreases, which allows air to rush in, okay, and fill the space. Simply because you just now have more room. When you inhale, you create more room in your lungs for then air to rush in. Okay, you've expanded your lungs, volume increases, pressure decreases. Now there's more room for more gas particles, right? It's not as tightly packed. So then air rushes in, and then you do all the, biochemical respiration process where you convert O2 into CO2, and then you breathe out, you release the pressure to prepare for the next filling. Okay. So then there's Charles' law, which now looks at volume and temperature. So what it tells us is that when we have a sample where the mass and pressure are constant, notice we're trying to isolate the two variables at a time. So we have to keep others constant. Mass and pressure are constant. We can say that volume and temperature have a direct relationship or a positive relationship. Okay. Volume and temp have a direct or positive relationship. And that is just so bad. I always used to think my handwriting was really good. And I'm realizing that this like flowy pencil thing is making my handwriting look very sketchy. Dare I say doctor level handwriting? So the equation goes is that volume in condition 1 divided by temperature in condition 1 is equal to the ratio of volume in condition 2 and temperature in condition 2. Okay. And so let's make that even simpler. If I increase volume, I'm going to also likely have an increase in temperature. And if you're like, whoa, that doesn't make sense at all, let's flip it. Okay. If I increase temperature, I increase volume. If I decrease temperature, I'm going to see a decrease in volume. That might make more sense to you guys, because if you think about it, if I increase temp, my particles are moving faster, which means they're going to want to take up more space. They're going to spread across space faster. But if I decrease temperature, my particles are moving slower, right? So that would kind of make sense that I would be less able to expand faster, right? I'd be less able to expand in general and take up space. Quick note, again, let me remind you, temperature is always measured in Kelvin for these gas laws. Whenever we talk about gases, you always want to measure temp in Kelvin. So how do we use Charles' law to explain something like a hot air balloon? Well, remember with a hot air balloon, right? You have a balloon, and you have a little basket, and you have fire. Okay? And so what we do is you have a lot of heat, fire, okay? What we say is that as temperature increases due to the flame, the gas particles' kinetic energy also increases and begin to expand the balloon. Okay, which really means that volume increases, right? So if you're like, wow, this totally makes sense, that's good. That's what you should be feeling. This is stuff that you experience every day in the real world. You just don't always think about it. So the third and final kind of isolated relationship between 2 out of the 4 variables is known as Gay-Lussac's law. Gay-Lussac is actually named after the 2 scientists who discovered it. Gay, which by the way meant merry back in the day, it meant happy, and Lussac, and I believe they were both French. So the law tells us that when you have a fixed mass or amount and constant pressure, okay, did I mean constant pressure? No, I think I meant constant volume. That's it. And constant volume. I was like, wait, I shouldn't be repeating. And constant volume, okay, we say that pressure and temperature have an indirect relationship. So mathematically, that means that pressure in conditions 1 and temperature in condition 1 have an equal ratio to pressure in conditions 2 and temperature in conditions 2. Again, here we see temp is measured in Kelvin. So let's put this now into language that we can understand. When I increase pressure, okay, oh my goodness, guys, that didn't make sense at all. I have a direct relationship. Okay, have a direct relationship. I'm too far into the video to start over, so we're just gonna, hopefully you guys didn't write too big. Pressure and temp have a direct relationship, because when I increase pressure, and I'm gonna actually start from the other side. When I increase temperature, I increase pressure. And when I decrease temperature, I decrease pressure. Okay, so let me repeat that now in one concise manner. Gay-Lussac's law for gases tells me that when my gas mass or amount is fixed and the volume is constant, I see a direct relationship between pressure and temperature, where if I increase the temperature, my pressure will also increase, the pressure due to my gas. When I decrease the temperature, my gas pressure, the pressure due to my gas, will also decrease. And here's why. When I increase temp, I have faster particles, more collision. When I decrease temperature, I have slower particles, less collision, less impact against whatever container is being measured, whatever limits, boundaries of volume are being measured, right? So how does this explain why water bottles implode on a hot day if you leave it in the car? So let's bring this into a tangible context. With increase in temperature, right, due to a hot day, right? If I have a quick and significant increase in temperature, then the particles in the air have a higher kinetic energy. And that increases the pressure of the air particles against the water bottle. And so what happens is then that what we call atmospheric pressure, the pressure of the air pressure, the atmospheric pressure, is now greater than the bottle pressure. And that results in your water bottle being crushed. Some of you guys might have heard of the crushed can experiment. If you guys went to a really cool middle school where you did lots of experiments, this would be the same principle. So notice that all of these laws, specifically the mathematical relationships of these laws, right? All the mathematical relationships here. Relationships of these three laws is used, or is, I guess you could say, expressed in final or initial versus final context. When there's been a dynamic change, right? When there's been a dynamic change to the environment. I started off with conditions with pressure 1 and volume 1, and now I am in another condition. How did that change? So here, these three laws can only be used. They express the relationship that holds true no matter what, but their mathematical relationship is used under the context of seeing a change in the environment and therefore predicting what my new pressure or my new temp or my new volume would be in another condition setting. Okay. And that's kind of how these three laws express the relationships between 2 out of the 4 variables at a time. But we do have one kind of giant combined law known as the ideal gas law that takes all 4 variables, amount, okay, pressure, temp, and volume, and puts it in terms of a static relationship. Given these conditions, what would I have, right? Not given the changing conditions, what would I get? But ideal gas law is a very much a static, unchanging, in a moment, static relationship. Okay. Oh, and I actually left a bunch of space for me to write this. It is a mathematical relationship between all 4 variables, all 4 factors under static conditions, under static or unchanging, under static, unchanging, in the moment conditions. And what the law tells us is that pressure times volume equals the amount of gas particles measured in moles times some gas law constant, okay, and temperature, okay? This gas law constant is known as the ideal constant. And we actually have many, many variables that we use depending on the individual variables of the 4 factors: pressure, volume, moles, and temp. I'm going to tell you right now, the most common gas law that we're going to use is this one, because we like to measure volume in liters, pressure in atmospheres, temperature in Kelvin, and amount in this new unit called moles. I'm going to delve into that later in unit 5. For right now, just know that there's a new unit. Okay, just accept it, take it. So that's kind of going to be our chosen R constant. Remember that a constant, okay, the role of a constant is to create a measured value, a value that relates many variables. So that's why you see that it's really important for any constant in any equation to have the same variables as all the other factors that you're comparing. So this is our what we call ideal gas law equation. And my only expectation of you, okay, is to understand how to plug and chug, to use it. If I give you information, if I give you 3 out of the 4 variables, and then also the R value, could you solve for any unknown, right? Basically algebra, okay? So, and I realize I'm gonna put that here. So, wow, I love how I talk over myself. So let's do a practice problem, okay? So we wanna calculate the pressure of, let's say, 1.82 moles of sulfur hexafluoride when it is at 285.6 Kelvin and 5.43 liters. So here, automatically notice you are working with a static, right? Static, unchanging conditions. You are given amount in moles, 1.82. You are given temperature in Kelvin, 285.6. You are given volume in liters, 5.43 liters. And you are asked to find pressure in ATM. Okay? So all I hope that you can do is you can say, okay, this is totally where I use the ideal gas law. It's a static relationship, and I'm given 3 out of the 4 factors. So I'm going to plug it into my equation, PV equals nRT. And I'm actually going to manipulate my equation so I automatically just solve for P. So I'm going to write this as P equals nRT divided by V. And now I'm going to plug in my values and chug out the calculations. We call it plug and chug. This is old school method, plug and chug, right? I give you an equation with variables. You plug in the variables that you know, chug out the calculations to find the unknown. So P equals N, which is 1.82 moles, times R, which is 0.08206 liters times ATM all over moles times Kelvin, right? I'm going to choose the R constant that has the same units as all my variables, times temperature, which is 285.6 Kelvin. Let's see if I can move this over so it fits a little better. Right? Okay. And I'm going to divide it all by my volume value, which is 5.43 liters. Okay. And let's see if I can quickly do this math. When you plug this in, 1.82 times 0.08206 times 285.6 equals 42.65. 0.654. And what's that on top? When I unit track, my moles cancel, my Kelvin cancel, and I'm left with 42.6 liters times atmospheres divided by 5.43 liters. And I simplify that even further, divided by 5.43 liters. And I get that my liters cancel, and my final value is that pressure equals, for the static condition of sulfur hexafluoride gas, that my pressure under these conditions would equal 7.86, okay, atmospheres. And notice when I track my units, I am definitely only left with atmospheres. So I know that I set up my variables correctly. So that's kind of what I expect you to be able to do if I were to give you an ideal gas law problem, is identify the variables, plug them into the known equation, and calculate out the unknown. The same can be said for these values. If I give you initial conditions and then I give you only one part of the final, you could be able to solve for the other variable final conditions. So that's all I have for you guys today. And oops, I see that I was a little unclear right here. The units must be the same as the variables. I see. The variables it is described, it is connecting. So let me make this clear. As the variables, the constant is relating. Okay, so sorry, kind of backtracking there, but best of luck. You have some workbook problems, and I'll see you all for the next day in school. Don't forget, you actually have a take-home lab project for this unit, because I figured this is a fun unit where you can teach yourself through experimentation. So make sure to read the instructions on the ideal gas law / gas laws project. You will be submitting a video to me. I also don't forget to submit proof in Canvas that you have completed this mini lecture. And we will have one day where I kind of check in with all of you guys. But for the most part, this is part of signing up for honors. It is your responsibility to grapple with the topic, struggle through it, and accomplish what you need. Feel free to ask questions. But I am confident that you guys can do this. So have fun doing the lab. Best of luck. Don't make your parents spend too much money. Okay, bye guys.